Welcome back to the next session in this Cornerstones of Material Science and Engineering course. So, like always, there will be two parts to this particular session. One is the content part, the other one is the andragogy / pedagogy part. So, I will start out by telling you a little bit about some concepts that are important for andragogy or pedagogy, and some things that I'll cover during this particular session. The first one is active cooperative learning, and this has been a continued thread throughout these sessions. So active cooperative learning has two very important aspects that are connected to learning: activity of the student and cooperation among the students. So hence active cooperative learning. So the active part or the activity part enables self-engagement, and hence it appreciates the individuality of the students. It also enables feedback between the teacher, the other students and the individual learner. The cooperation among the learners enables knowledge sharing, ideation, and hence creates an environment and an ambience where learning is facilitated. Again, at some level, arguably it is creating a scaffold structure within the framework of a classroom. The next one is guided reading and writing. So there should be some kind of reading and writing exercise as part of any of the ACL classes. By that what I mean is, it is important for the teacher to sort of provide guidelines that enables reading and also writing. And as I have told earlier, writing is an important activity because it involves the learner. It enables direct participation from the learner, which is highly valued. And because writing itself can be a very contemplative, reflective activity, it enables learning. Many classes are actually moving away from writing, and I think it is a problem at some level because of the fact that one very important mode of engagement by the student is eliminated when you eliminate writing. So writing of some form, even if it is tech enabled, if it is on a laptop, must be encouraged in modern classrooms. The next one is participatory learning and action, and I have given a formal definition for that here. Participatory learning and action allows engagement with learning communities. It uses participatory and visual methods with natural interviewing techniques and intends to facilitate a process of collective creative thinking and critical thinking and learning. It enables learning behavior, attitude and knowledge sharing relationships that are relevant for modern life and conditions. So many of you will agree that in the modern world, learning is a continuous process. There are very cognitively demanding jobs out there, and many of our students will go on to get many of these cognitively demanding jobs that require lifelong learning. And hence we ought to encourage certain attitudes and behaviors towards learning. And participatory learning and action framework encourages a certain kind of knowledge sharing, an attitude of continuous learning, an attitude of learning and teaching, a democratic attitude towards education, knowledge and continuous growth among students. And this, I believe, is very important for surviving in this 21st century, a century wherein there are a large number of jobs that require participatory action. And the classroom setting can be a place wherein they can simulate such real workplace environments, and we as teachers can facilitate that. So I really believe that participatory learning and action approaches can also be of tremendous value to teachers who would like to create more meaningful teaching learning environments. And not only that, you might have noticed that I go around asking almost interview-like questions to students. What do you think about this, and what do you think about that, and what do you think would be an alternative way of thinking about this particular concept, and what do you think is an example of this, and so on. So this kind of an interview approach also enables active participation among students. They deliberate in the classroom environment, and that is very valuable for their learning. And for you as an educator, you get direct feedback and also opportunities to provide guidelines, opportunities to do both creative as well as critical thinking with your students, promoting creative and critical thinking among your students. This becomes possible if you actually achieve this kind of a classroom environment. So briefly, Participatory learning and action, this is the first time I am talking about it. I use techniques from participatory learning and action in my classrooms, and I believe you will also benefit from using participatory learning and action and active cooperative learning exercises in your own classrooms. The last thing that is very important, and this is something that I have discussed in the last class, but here I will give you a formal definition. Vygotsky, this is not a direct quote from Vygotsky, but it's from a paper that quotes Vygotsky. And in this particular paper, I have found a fairly reasonable definition of the zone of proximal development. So it is defined as the distance between the actual developmental level as determined by independent problem solving and the level of potential development as determined through problem solving under adult guidance or in collaboration with more capable peer. Here capable is to be interpreted as more experienced peer, that's all. Okay. So this is really what I meant in the last session when I said, let us say that a learner is allowed to learn on her own. Let us say that you have a certain, they have a developmental stage that they can achieve, and then you handhold them and they actually achieve a higher level of development. This gap is basically the zone of proximal development and the zone where the instructor, the teacher, can make an enormous difference. And in fact, if you can widen it, then your role is actually widened. Your role becomes more and more important. And here is precisely where your experience needs to be brought to the table. Greater your experience, greater will be the zone of proximal development, and larger will be the scope of your engagement with the students. So teachers, as a consequence, also have it in their responsibility list. One of the key tasks of their responsibility, the task that is associated with their responsibilities being their own continuous growth, their own continuous development and experience gaining, because that enables them to actually expand the zone of proximal development for their students. Okay. So with that, we go on to the content part of this particular lecture. So I will walk you through some electrical, magnetic, optical and acoustic properties of materials, and we will do some case studies based on that. Just like last class, we use some figures to sort of creatively and critically think about applications. This time also we will use some props in order to see how we could use electrical, optical, magnetic and acoustic properties of materials, or how we could interpret some of these properties. Suppose we have data. So I will give you some data and you will start interpreting it. And even before that, we will look at some basic definitions associated with electrical properties. So resistivity, susceptibility and breakdown field. These are three words that I am going to introduce you to right now. So you will see the formal definition here. Alright, so you will discuss the formal definition among yourself, maybe connect it with concepts you have learnt previously. And then I will show you some data and we will start some exercise. So to begin with, you engage with one another, discuss resistivity, and you will see that there is a relationship between resistivity and conductivity, and you have seen the units of conductivity. So what would be the units of resistivity? Number one, you have seen the values of conductivity associated with metals, ceramics, polymers, conductors, insulators, semiconductors. So what would be the values associated with resistivity, okay, of metals, or let us say conductors, semiconductors, insulators, okay. So that is one question. So I am defining resistivity as the inverse of conductivity. You have seen conductivity values for conductors, semiconductors and insulators. So what would be the resistivity values? So you will have to write down these resistivity values. You will have to discuss this among yourself. Discuss susceptibility. You can recall something called the Gauss's theorem, which you might have studied. That is flux density and electric field correlation, something you might have studied in your high school physics. So if you can recall, you are welcome. At the very least, I expect you to know a little bit about dipole moment. If you don't remember, you are welcome to use your favorite search engine to define dipole moment, polarization and so on. And then breakdown field, okay. So, and the unit associated with breakdown field. The hint is breakdown field is an electric field. So, what do you think would be the unit associated with the breakdown field? Okay. So, three questions. One is resistivity. What will be the values of resistivity associated with conductors, insulators, semiconductors? Second question, electrical susceptibility. Connect it with Gauss's theorem as you have studied it. At the very least, look at the correlation between flux density and electric field. Third question, breakdown field. Okay, what would be the unit of it? The hint is it is an electric field. So what would be the unit associated with breakdown field? So you have between 2 to 5 minutes. So I'll walk around, and as and when you make progress, I will stop and we will have some anchored discussions. Okay? Yes. So do you understand the questions? So the first question is values, typical values associated with conductors, semiconductors, insulators, the resistivity values. And the resistivity is inverse of conductivity. Rho is equals to 1 over sigma. Sigma values you have already written down in your notes. Okay. You understood the first question? So rho, which is resistivity, is 1 over sigma. Sigma values you know for conductors, semiconductors, insulators. So what are the rho values? That's the first question. And you will give me those values. Okay. So you can go back. You can also use your favorite search engines. Let us say metals. What are the typical values for sigma, and hence what will be the value for rho? And use your calculators if you wish, because you have to do 1 over sigma. Once you have a number, you can share the number with him, or once you have a number, you can share the number with him. It will be nice if you do it for conductors, you do for semiconductors, you do for insulators, something like that. That way very quickly the table gets done. You understand? So you can do for conductors, you can do for semiconductors, you can do for insulators. That way the table gets ready soon. Okay? So Bodhi, you will be responsible for going and populating that by asking the people in this particular class. So now it is 4:10. When it is about 4:12, you can go to the board and you can ask people and you can start populating it. Remember, there will be some range for sigma and rho. Some range. That's all I am looking for. Are you load sharing? So one of you does for metals, semiconductors, insulators. So you can do right now only for that. Then you go to the board and ask people to give some numbers, and let's see whether they are reasonable. You are load sharing? You're doing some load sharing? Good, good. So you have some numbers. So Bodhi, now you can go to the board and start filling that table. So sigma, rho, conductors, semiconductors, insulators, just give the ballpark windows of numbers. So you can ask your friends here and let's see what they have to say. So start with conductors. So Saurav or Naveen, between the two of you can.
Silver, the resistivity is 1.59 and 10 to the power minus 8 ohm. 0.59 into.
But remember, you have to give me a range for rho and sigma. Do you want some more time for finding out the ranges?
Range is like for metals it will be in the range of 10 to the minus 8. So particularly 1.59 into the minus 8 ohm meter is for silver. For copper is something like 1.68 into the minus 8. So this is the order of 10 to the minus 8.
Yeah, but you will have to give me a range. It is a 10 to the power of minus 8 to 10 to the power of minus something. You understand? So you can look at a range. So Bodhi, do you want to go back? I don't think people understood the question yet. Why don't you write down? Why don't you write down? You understood? So for example, let me give you an example. Let me tell you. For semiconductors, the sigma value varies between 10 to the power of minus 3 to 10 to the power of 3 Siemens per meter. Did you understand? So the range is 10 to the power of minus 3 to 10 to the power of plus 3 Siemens per meter for semiconductors. So that is a range. And hence by extension 10 to the power of 3 to 10 to the power of minus 3 ohm meter would be the resistivity values for semiconductors. So I just gave you 2 entries for that particular table. I am asking you to give me the remaining 4 entries. So ballpark, that's all I am looking for. So whenever you give numbers, the units are very important. So this is 10 to the power of minus 3 to 10 to the power of 3 Siemens per meter. And Siemens per meter is exactly same as mho per meter or ohm inverse meter inverse. It's exactly same. So here it will be 10 to the power of 3, 10 to the power of minus 3 ohm meter. You understood? I am just giving you some ranges. It could be 1 or 2 orders of magnitude here, there, it doesn't matter. But I am looking for ballpark.
For insulators,
For insulators, tell me the resistivity. Ten to the power of 12 to 10 to the power of 21 typically ohm meter, that is correct. So by extension this will be 10 to the power of minus 12 to 10 to the power of minus 21 mho meter inverse. Agreed? Or Siemens meter inverse. Alright, now for conductors please, above this. So it will be greater than 10 to the power of 3 Siemens per meter, and this will be greater than 10 to the power of minus 3 ohm. 10 to the power of. So this 10 to the power of 3 to 10 to the power of minus. Ha. No, this will be greater than this value. Sorry, this will be less than. This is greater than, so this has to be less than. Correct? Okay, so this table is useful. One of you can take a snapshot of this table and send me by email. So please take a snapshot of this table. Likewise, I got a snapshot of the thermal conductivity table that you made last time. That's here. It's based on numbers you gave me. Okay, so CB, CP. So this one is actually 1. Okay, this one is 1. See, kilojoule per kilogram per Kelvin, and so on. So these are your thermal conductivity tables. So I expect you to remember the ballparks. As you go from, let us say, a ceramic to a metal to a polymer, how do the trends change for thermal conductivity? Similarly, as you go from conductor to semiconductor to insulator, how do the rho, sigma values change? This is very important. Okay. So another thing I want you to notice, see, between 10 to the power of 12 and 10 to the power of 3, there are ranges. So doped semiconductors usually will have these conductivities. So doped semiconductors can actually have a fairly wide range associated with them. Okay. So in principle you can add one more row here, doped semiconductors, and they can actually have conductivities between this to this value to this one. Okay, so a wide range of compound semiconductors, doped semiconductors, intrinsic semiconductors. So you, based on the semiconductor you're dealing with, you can actually have some values between these two as well. So that is essentially because of the tunability of semiconductors. So you can have, so between these two you can actually have wide range of semiconductors. Okay. Okay, so that is about resistivity and conductivity. The next question is about flux density, electrical flux density. That is, if you recall, D is equals to epsilon naught, epsilon R into electric field, E. All right. D is equals to epsilon naught, epsilon R into electric field, and that epsilon R can be written as 1 plus susceptibility. So let me erase this. So and from your high school physics, you recall that this is how the Gauss's theorem comes about. You know, the integral E dot ds expression comes from that, or integral D dot nds expression comes from that relationship. But D, which is the electric flux density, will be epsilon naught, epsilon R, which is called the relative dielectric constant, or the relative permittivity it is called, into electric field. This is a vector, this is a vector. So this one is called the relative permittivity, or it's called the relative dielectric constant, and this one is called the permittivity of free space, or the vacuum permittivity, and this is a constant. All right, it's a constant. So I want you to use your favorite search engine and tell me what the permittivity of free space is. Value. And this epsilon R can be written as 1 plus chi, and this chi is called susceptibility. That's what I have written there. Dielectric constant epsilon R is equals to 1 plus chi, and that is the susceptibility.
8.85
Correct. So epsilon naught, which is the permittivity of free space, is 8.85 into 10 to the power of minus 12. Is unit important there? How much is it? No. What is the unit? Unit. 8.85 into 10 to the power of farad per meter. Correct. What is farad? The unit of capacitance. Very good. Next is breakdown field, the electric field at which a dielectric begins to conduct. That means an insulator starts conducting when you apply an electric field greater than the breakdown field. Now it's electric field. So what is the unit of breakdown field? Volt per meter. Volt per meter. Very good. So now let me show you some data. So it's a classroom exercise. Look at the table below. Do all values fall within reasonable limits? Do you find any errors? So look at this data and tell me whether these numbers are reasonable. We made this table, no, for semiconductors, metals, insulators. Okay. Have I changed any number so that it becomes unreasonable? That's my question. So for example, copper, you know, is a metal and hence it's a conductor. Graphite is a conductor. Seawater is a conductor. Silicon is a semiconductor. Rock salt is an insulator. Distilled water is an insulator. Marble is an insulator. Mica is an insulator. Paraffin is an insulator. Fused quartz is an insulator. So do the numbers given here correspond to reasonable expectations based on the table we have given you or the table that you have arrived at, or is there some number that is wrong? That's my question. No, discuss with one another, please. Please discuss with one another. Is there any number that is unreasonable? I just told you which one is a conductor and which one is a semiconductor and which one is an insulator. Does it map well to the table that you have made? That's my question. Remember, they are all approximates. Silicon, is it reasonable? Yes. Rock salt, it's an insulator. So that's reasonable. Rock salt is also reasonable. See, the resistivity is greater than 10 to the power of 3 ohm meter. Seawater is 10 to the power of 0, that is 1 ohm meter. So seawater is shown as 1 ohm meter. So the seawater, the way it is shown here, it's more like a semiconductor. You anticipate a much higher conductivity there. You can anticipate much higher conductivity there. Okay. Next is graphite, 10 to the power of 6. It's a conductor. No question. 10 to the power of 6 Siemens per meter. That's reasonable. Graphite is a conductor. Copper, 10 to the power of 7 Siemens per meter. Reasonable. Next is only rock salt. Okay, rock salt conductivity is 10 to the power of minus 4. That's just about reasonable. I mean, I expect that number to be a little smaller. Okay, this is likely to be some kind of doped rock salt because it has some impurities. I expect this number to go down. This number is about reasonable. This number is reasonable. This number is reasonable. This is reasonable. This is reasonable. The only problem cases I am anticipating are seawater and rock salt. So only those two numbers seem a little off. Okay, based on the table that we have made. Okay, good. Next is, here is a table of breakdown fields. Why don't metals figure here? So this is a table of breakdown fields. This is from Wikipedia. And please notice the unit of field is megavolt per meter, the way it is written. So that is volt per meter. So for example, 0.15 megavolt per meter would be 0.15 into 10 to the power of 6 volt per meter. Okay, you understand this? So notice that there are all these materials given, none of them are metals. Why is there no metal here? Is breakdown field defined for an insulator, semiconductor or metal? Insulator. So it's actually defined primarily for insulators. So it is the field beyond which something that doesn't conduct electricity starts conducting electricity quite dramatically. Metals conduct electricity no matter what field you apply. So breakdown field doesn't hold true for metals. It is not defined for metals. But take a look at some of the numbers. Now air, look at that. Air is an insulator. What is the breakdown field associated with air? 3 into 10 to the power of 6 volt per meter. Glass, it is about 10 into 10 to the power of 6 volt per meter. And typically that is true for a wide range of glasses. Okay, silicone oil, it's about 10 to 15 into 10 to the power of 6 volt per meter. Rubbers, And this is also true for a large number of plastics. It can be fairly high, you see, 20 into 10 to the power of 6 volt per meter. Fused silica, see, fused silica is larger than window glass. Fused silica, it actually survives a very large breakdown field. Did you notice that? Fused silica survives a very high breakdown field. And then look at diamond, survives a very, very high breakdown field. It is essentially gigavolts per meter. So it's very hard to break down diamond. PCT is an insulator, it's about 20 into 10 to the power of 6 volt per meter. And this one is actually a dielectric that has piezo action. It does depend on temperature. Very good question. Dielectric breakdown does depend on temperature. So this one is at room temperature. Very good question. So next is some values of relative permittivity at a fairly low frequency. That means, and this is also at 1 kilohertz, the value you get is almost same as the static values. So I am giving you the relative permittivity. Permittivity, remember, is this one, epsilon r. So I am giving you the relative permittivity for a few materials. Alright. And this is very close to the static values. What are some trends that you observe? So I have a bunch of materials here. And I am showing you the relative permittivity. What are the trends you will observe? So discuss with one another some trends. You must have studied in your general chemistry or something few details associated with the chemical composition of these materials. Alright. To do the composition of these materials, the chemistries of these materials correlate with the dielectric constant. That is the question. You understand? So discuss this with one another, please. So let me shrink this a little bit so that you get to see where I got this from. So discuss with one another what chemistries correspond to high dielectric constants, what chemistries correspond to low dielectric constants. So discuss with one another, please. Is it just chemistry? Is it also crystal structure? It might be important for you to think. Crystal structure is atomic arrangement. So what are your observations? What trends are you noticing about relative permittivity? What kind of chemistries give rise to high relative permittivity? This is low frequency dielectric constant. Correct. So if you have atomic composition such that there is higher dipole moment possible in the material, it results in higher dielectric constant. And of course, if the atomic arrangement is such that there is dipole moment possible because of just atomic arrangement, then that would also increase the static dielectric constant. Very good. Next, did you find the trend? Yes.
Polymers are very low.
Yes, polymers tend to have very low dielectric constant. That is true. Not all of that, all polymers have low dielectric constant. There are some that have fairly high dielectric constant, but the polymers given here, and in general, a large number of polymers have low dielectric constant. Correct. Yes.
And some like semiconductors.
Correct. Correct. A large number of semiconductors have fairly high dielectric constant. So silicon, is that value given there? No, it's not given.
Yeah,
So,
so
that's about 11. Yes, that is correct. All right. And notice that graphite is also about the same.
Yeah.
Right? Yes. And then you will find that there are those titanates, strontium titanate, barium strontium titanate. Those are all highly polar materials. So they actually are polar not only because of their composition but also because of their crystal structure. They belong to something called the polar crystal structure type. Alright. And then look at that hydrocyanic acid. It's a highly polar material. It's a highly polar acid and hence its dielectric constant is very high. So typically dielectric constants increase if the polarity that is embedded in the material is high. So that's one major take home. Okay, here is a classification of materials based on complex permittivity. This is a toy problem for you. I mean, this is at a slightly analytic level. So the permittivity here, as defined here, can actually become a imaginary quantity. I won't explain why here. Later on, there may be a session on that. But this can actually become a complex quantity. That means there can be a real part and an imaginary part. So I can actually define a ratio epsilon double prime divided by epsilon prime. Okay, and based on the ratios, I can define the material as either a lossy material or a lossless material, a good dielectric, and so on. So look at this. All right, how will you get this kind of data? Epsilon prime and epsilon double prime. Can you discuss an experiment by which you can get epsilon prime and epsilon double prime? Because clearly, in order to determine whether the material is lossy or not, I need the complex dielectric constant. It is not just the low frequency dielectric constant, it is not just the static dielectric constant, which is a real number, but an imaginary number that is very important. This is very essential for waveguide applications and so on. Suppose I want to design an optical fiber, I need to know whether or not the material that I am using is lossy. If it is lossy, the light will die down very quickly. You understand? So can you think about designing some experiments that will give me information about this ratio epsilon prime divided by epsilon double prime divided by epsilon prime? You understand? This is divided by epsilon prime. Divided by epsilon. And remember, if it is infinity, it's a perfect conductor. That means there's perfect loss. That means there's no electromagnetic radiation that is going through that material. That means it becomes a Faraday cage. So if I actually enclose this classroom with a metal, a perfect conductor, no light will go out of this material, this room. You understand? So that's the Faraday cage. No light can come from outside to inside. So that's a Faraday cage. I have completely separated out electromagnetic fields. So if it is infinity, epsilon double prime goes to infinity, I basically create a Faraday cage, which is something you have studied in your high school physics and so on. It basically enables you to isolate electromagnetic fields. It enables you to cut electromagnetic fields. You can cut it out. Okay, suppose I have this room covered with a perfect metal, no electromagnetic radiation will come from outside to inside. No electromagnetic radiation generated inside will go outside. You understand? If it's a perfect conductor. If it is much larger than 1, it certainly is a good conductor. If it is approximately 1, then they are comparable. It is somewhat lossy. But it will conduct. There will be light that will actually go through it. But it's somewhat lossy. But much lesser than 1. This is much smaller than 1. It basically is not as lossy. Okay? And it tends to be a poor conductor. It's perfectly zero. It's a lossless material. No loss occurs. Absolutely no loss occurs. So whether a material is lossy or not is determined by epsilon double prime divided by epsilon prime. Okay. So my question is, can you design an experiment to determine epsilon double prime and epsilon prime? Number 1. Number 2, do you think this epsilon double prime divided by epsilon prime is frequency dependent? Okay. So why don't you discuss with one another? You understand the question? So can you think about an experiment to determine epsilon double prime divided by epsilon prime? Number 1. Number 2, do you think this ratio is frequency dependent?
Lossless medium
Means if you are passing an electromagnetic
so there is no loss.
wave through the system, light of varying frequencies. Suppose at a particular frequency epsilon double prime is very low. That means that light will actually go through. You understand? So I have a material. This material has some epsilon double prime divided by epsilon prime. I have found that epsilon double prime is very, very high. That means it will be perfectly lossy. That means I am going to impinge light, all the energy loss will occur here itself. No light will go through. You understand? On the other hand, epsilon double prime divided by epsilon prime, it's very, very small, much smaller than 1. That means there won't be much loss here, so it will propagate. If it is perfectly zero, no loss occurs anywhere. It will just go through. Whatever is yours sending in here will come out here.
So here conductor.
Does that loss depend upon frequency? Of course. So epsilon double prime divided by epsilon prime is highly frequency dependent.
So how do we connect this conductor, perfect conductor and loss?
So a perfect conductor is something that conducts electricity perfectly. Okay, that means it responds perfectly to an applied electric field. I mean, you have near infinite current when you are applying the smallest amount of electric field. So what happens as a consequence is, if you are having any electromagnetic radiation incident, sigma goes to infinity. If sigma goes to infinity, over just an infinitesimal distance, the energy contained in the light is actually dissipated. So the higher the conductivity of this material, lesser is the distance of the material through which that light will percolate. So if the conductivity is infinite, zero distance into the material, light basically stops propagating. It basically gets dissipated in the skin itself.
So that's why you get perfect loss.
Perfectly lossy conductor. So when something is a perfect conductor, it becomes perfectly lossy also. You understand? You understand? So now that's why I said, if I am going to engage this room in a perfect conductor, I am going to use a perfect metal to enclose this room. No light from outside will come inside. No light from inside will go outside, because if light is attempting to go outside, within the first infinitesimal distance of that particular thickness of that particular material, the light will actually undergo dissipation. It will not go through.
What, like,
Huh?
I mean, what kind? Dissipation is what kind?
Heat. Heat is the most obvious consequence of that loss. So light will impinge, it will get dissipated in the form of heat, and as a consequence, light will not propagate. It will just get lost in the form of heat. So any light will get converted to heat if it's a perfectly lossy material. You understand? You follow? So an experiment can you do this as a homework? An experiment to detect epsilon double prime divided by epsilon prime. Those of you who are studying chemistry, chemical engineering, etc. would have studied impedance spectroscopy. This is perfectly analogous. Alright? Okay. So this is homework for you. Determining epsilon double prime divided by epsilon prime. Okay, can the electrical properties of a material be used to determine composition, granularity or hardness, or maybe fracture in the material? This is a question. Just discuss this question with one another. Can I use electrical properties of a material to determine composition, granularity, hardness of a material? Is it allowed, disallowed? Can you be creative? Okay, discuss with one another, and you can use your handout and the hint given in the handout to respond to the question. So there is this handout, you can open that question. So feel free to read the hint and give me a response. The hint is this abstract from a paper. Can I use electrical properties in order to determine things like hardness or granularity of a material? Yes, that's correct. And in fact, this is used for non-destructive evaluation. Without even destroying the material, I can actually measure electrical properties under changing magnetic flux. Look at eddy currents. If the eddy current loops are very large, eddy current losses are very large, it tells me something. Typically, if the eddy current losses are very, very high, then that means the conductivity is very high. Eddy current loops are very large. Okay. So if there are cracks, the eddy current loops become smaller and the loss will change. And so by benchmarking what amount of eddy current corresponds to what amount of granularity, or what kind of compositional fluctuation or presence of a fracture, I can determine the presence of each of these, signatures associated with each of these. And in fact, this is used for non-destructive evaluation. What is eddy current? Eddy current is the current that is induced in a material when I change the magnetic flux. and this is expected due to Faraday's law of induction. So if I have a material, I am applying a changing magnetic field across this material, I will end up seeing some surface currents, and these surface currents are set up in directions so as to prevent this change in magnetic flux density, you understand, and as a consequence there are current loops that are generated. Now these current loops will be very large if the conductivity is very high, but any change in composition, any change in granularity of the material, or any fracture can change the resistivity of this particular material, and hence I can just observe the eddy current loss in the material and correlate it with composition,
So more any kind of
fracture
fracture.
or granularity. Anything that can be correlated with conductivity or resistivity can be correlated to eddy current losses, and hence eddy currents are very widely used. Similarly, in petroleum pipelines, eddy current losses are used to determine the presence of micro cracks.
So eddy current is measured by
Usually in this particular case it is loss, it is heating loss that you actually measure. So no, because it's a circular current. So it is a current in the material, on the surface of the material. So you can only pick up the temperature signals. You can only, so if the local thermal fluctuations can be picked up, that can give you a lot of information about what is happening locally. That's really the idea. So wherever you want to study fractography or presence of fracture or whatever, there you go and basically in the absence of the fracture, in the absence of granularity or whatever, you would do the eddy current measurement. Look at thermal signature, put it through its life, put it through its operation, and then study what will happen there locally when you are setting up eddy currents by just changing magnetic flux around it. That will give you some idea as to what is happening. And if the experiment is very properly done, you will get a lot of information about fracture and so on and so on.
It is for only surface current.
Surface currents. Eddy currents are purely surface currents. Agree. So hence eddy current probes are very widely used for determining this. So eddy current, and it's also called the Foucault current. Okay, Foucault is, it's a French name named after Foucault, the French scientist who studied this extensively. But the direction of these eddy currents are set up based on Faraday's law of electromagnetic induction. Okay, and eddy current testing is widely used in order to study the changes that are occurring to the material in operation, for example, whether there is grain coarsening, whether there is some kind of fracture in the material when you are putting it through operations and so on, can be studied by using eddy current testing. One of the big advantages to it is that it is a perfectly non-destructive testing approach. Okay, it's a perfectly non-destructive testing approach. That's the big advantage associated with it. And you don't need a ferromagnetic material for this. It can be any material that has some conductivity. Okay, because as long as it is just any material, suppose I take this material, it's not a magnetic material, let's say the surface of this is plastic, but if I am changing the magnetic flux associated with it, there will be some eddy current. But if, because it's a resistive material, the eddy current loop will be very small. If I make it progressively conducting, the eddy current loops will be larger and larger. You understand? You follow? Okay. Next is magnetic properties, acoustic and optical properties. I will stop here because I think we have covered quite a bit of ground for this session. Alright. So to summarize, as far as the andragogy and pedagogy is concerned, we discussed active cooperative learning, guided reading and writing. So today, for example, we did some guided reading and writing. I actually asked you to do some reading on your own in order to come up with trends of your own, observations of your own. I gave you some table of data and asked you to come up with trends, assessments of your own, gave you some reading material, and without describing non-destructive testing approaches, eddy current testing approaches, I asked you to think about applications for the same and so on. Then participatory learning and action and zone of proximal development. Okay. As far as content is concerned, we covered electrical and electrical properties. We did not even cover magnetic properties, all right. But we will come back to this in the next class. But we did do some case studies. Eddy current testing was a case study for that. Looking at tables and trends was another case study. Then distinguishing between semiconductors, conductors and insulators as far as rho and sigma is concerned were all case studies that you carried out, and you arrived at the value on your own. So Hopefully this will help all of you. So with this we are done with this particular session. We'll meet you shortly. Until then, have a good time. Thank you.